Okay, so hello again for this last session of PDC, I believe. Just to understand the audience here, who's been here for the previous sessions already? Most of you. Some of you have not. Okay, so that's going to be interesting. This session follows the first few sessions that we've had this morning, but it's going to be actually quite different. For those of you who have not been part of the first two sessions, I think you can get some information out of it regardless. So it's self-contained in nature, but it will reference some of the stuff potentially done in the first two. But if you haven't seen them, it's okay. What we thought we would be doing for this last session is taking a much lighter tone. So as I mentioned in my first session, you've seen, 50,000 slides, 2 million demos, learned 200 technologies. We thought that for this last session we could have some maybe not some fun, but at least some different perspective on things. And I just wanted to warn you that we will not be discussing much technology. We'll be not doing a lot of core programming or anything like that. We will be looking at this cloud thing, if you will, from the lenses of someone who is more business-oriented, and not only understanding the physical implication of the cloud that sometimes we forget, but also some of the business models that seem to be happening out there and the implication from an architecture perspective of those business models that we might see. So I wanted to start the presentation warning you and telling you that this rating is DG13, which is developer strongly cautioned. There will be a very limited Visual Studio wizardry in this presentation, and some Excel spreadsheet might even be seen in this presentation. So as long as you're happy with this, I will continue. For those of you who cannot bear this rating, feel free to go and check if there are other sessions that are more appropriate for your taste. But one thing I don't want to is having the evaluation form at the end and say, oh, I thought this was a technical session. So now that we agree, let's start. As I mentioned, when we build software, especially when we've been building it in sort of the current scenario, we sometimes forget that we're not in a lab. And I've been doing this mistake myself many times. I sometimes assume that bandwidth is infinite, that bandwidth is free. Sometimes I forget that there is a distance between the consumers and the provider of that particular service. I forget that we live in a world where there are laws and regulations. So what I wanted to do in this final presentation is really introducing and discussing through some hard data that we've collected that the world we live in, the world we build applications for, has physical constraints, has monetary constraints, and has policies or regulatory constraints. So I wanted to go through some of those at a higher level, maybe injecting some humor into this, hopefully, and discussing some of the architectural implication of those particular constraints. So at the end of this presentation, I think that we will all have a better sense of what is really happening in the world in terms of physical constraints, business models constraints, and policy constraints, having a hint and an understanding of how we might have to build applications differently because of that. So let's start with simple things. Let's start with two annoying physical limitations. There are many more, but let's start with two that we are seeing every day. One pesky little limitation, of course, is the speed of light. Something that, unfortunately, we cannot do much about, but is there. So speed of light is actually quite fast, 300 kilometers a second, or 186,000 miles a second. Actually, the speed of light is lower in fiber, 35% lower, but it's still very fast. But even at those speeds, a typical ping from the US and Australia is 0.15 seconds, which means that if you, for instance, do a website that gets an image, acknowledge, gets an image, acknowledge, gets an image 6 times, you're just having the person waiting for a second. Again, this is something, as I said, starting very from the basics, understanding that latency is a fact of life, regardless of the bandwidth you have. This is just the time you have to go and fetch something that you might need and display and come back. The other physical limitation that we have is Shannon law. Shannon law that says that the capacity of a pipe is bound by the logarithmic of the signal-to-noise ratio. And in this particular instance, logs are not very good for you. Logs are basically saying that you need to double the signal-to-noise ratio to get an extra B, if you will, the formula, which is how many hertz you have available in your channel. So this particular law here and the previous one basically says that latency in distributed systems are something we need to be aware of, that bandwidth is not infinite, and it's not free either, but we'll be discussing this in a few minutes. So before we continue and see some of the implication of that, it's important to understand that latency is not bandwidth. Latency is, if you think of it, the length of a bridge that you need to cross. And bandwidth is how wide the bridge is. It doesn't matter how many lanes you have in a bridge, you still, for one car, need the time that it takes to go on the other side. So something that often I see in my conversation, and maybe that's something very simple and obvious to you, but that there is this assumption that bandwidth, if I have more bandwidth, things will get better. Well, it will only get better if it's a throughput problem. If it's a latency problem, you can have as much bandwidth as you need, you can have as many lanes, if you will, you're still going to have to do, well, actually, there's nothing much you can do about the latency apart maybe being less chatty. Instead of going and fetching items that basically you pay your fixed cost of latency every time, maybe going in a more chunky approach, get all the data that you need out of it in one request, and display all back out into your environment. So again, thinking about bandwidth is on capacity, and latency is about going on the other side. And this is a quote and a joke that we tell sometimes. It's like a FedEx truck driving from Seattle to Los Angeles with 10,000 terabyte disk has huge bandwidth, but has very bad latency. So I think this is something that one has to accept and include in the thinking, but sometimes those arguments are often intermixed. And when you think about building cloud-based applications, something that is very different from building applications that live in the data center is that latency becomes a real fact of the application. Cloud infrastructure does not run next to your user, does not run next to your computation environment potentially. If you have storage that is far away, you have to think about the storage far away, including the latency of the fetch, as opposed to just assume that it's just on the blade, just under that particular request. So let's go and continue about more the bandwidth and cost and limits. I was looking at what some of the services available out in the internet. And if you think about internet radio, it's broadcasted these days, at least in the US, at 64 kilobits per second, which if you were listening to it 24/7, all the time, you basically would be downloading 21 gigabytes of data every month. If you were to watch YouTube 24/7, then you would be downloading about 166 gigabytes of data every month. And if you were watching HDTV 24/7, then you would be downloading about 1.2 terabytes of data every month. Okay? Now, if you compare that to the bandwidth that you have available to you, some have 1 megabit per second, some have 4 megabit per second, some have 20, and if you live in Hong Kong or Korea, you have much more than that. But depending on how much bandwidth you have, the time to download 10 gigabytes at full bandwidth varies dramatically. Or even the max download you can have per month also varies. So again, with simple math, you can see that if you have 4 megabits per second, you will be actually downloading everything you can from the left-hand side of the diagram, which is internet radio, YouTube, and HDTV. So all that is fine and dandy, and things are happening, except something that is currently happening in the US, and that has happened in other countries before the US, is that the service providers, the ISPs, are capping the number of gigabytes you can download. Comcast, as an example, is now giving you, as a subscriber, if you are a Comcast subscriber, 250 gigabytes a month of total data that you can download. And if you happen to live in Australia, most of the service providers give you only 20 gigabytes per month at your full speed. And then you basically are not shut down, but you go back to dial-up mode, which basically means you're shut down. And if you start looking at those numbers, and if you have 250 gigabyte total downloadable content per month, which is the equivalent for 250 to 772 kilobit per second of constant pipe, you would be listening to the radio all the time. That would cap 80% of your total usage. If you were watching YouTube all the time, then you would be capping 2/3 of your capacity. And if you were watching HDTV, then you would be going 5 times beyond what you actually are allowed to before paying penalties or paying extra to the providers. If you're in Australia, you can barely listen to the radio. Why is this important? It's important because based on what you are offering, you might be assuming that the underlying infrastructure is available to you for free with no limit. If you are one of those video service companies and you assume that the underlying infrastructure is free to you, then you're going to be surprised when caps are getting introduced. So those are the things that, one of the things I wanted to introduce, and we'll see some of the example here, because on one hand, 250 gigabytes seems a lot. If you look at it, 250 gigabytes a month allow you to send 50 million email a month. You know, I send quite a few emails, but I guess 50 million is a nice cap. I can live with that. I can download 62,000 songs every month. So even for the most, bear share or any sort of those network-friendly illegal things, which I don't, I don't use it, I don't condone. It's already a big limit here. You can also download 125 standard definition movies, which, how much movie can you see? But the thing is, on one hand, most of the people, the 99% of the population, seems to be agreeing with this. So I don't see the cap being changed by Comcast, for instance, because they will not be having millions of customer calls saying, hey, I cannot do what I need to do every month, because 99% of the people, if not more, will be able to do anything they need to do that month within that cap. There will be, of course, some people not very happy, but the pipe owner have no incentive to increase that because the vast majority of the people will be part of that environment. So another thing to think about is that if you're a company that needs a lot of bandwidth, typically video, or you have actually a lot of customers there, and assume that free and unlimited bandwidth is underneath, you could be hurt because of just those numbers. So let's continue. Let's find some monetary explanation of that. So I went on the web, I did some searches, and I did some averaging, and I found appealing services that meet my requirements, and they will be charging me 15 cents a gigabyte for storage and 17 cents a gigabyte for the bandwidth that I'm using out of that particular service. I said, well, that's pretty cheap. I like it. Well, let's see. If I'm downloading video 24/7 and I was to buy and pay at those rates instead of having the flat fee that Comcast or the ISP of your choice is giving you, by watching YouTube all month, I would be paying about $28 a month. And if I was watching HD movies all the time, I would be paying $220 every month. Hey, if I'm start paying for bandwidth, I might be more conscious about the type of download that I make. Again, this is not something that is intuitive for many of you, because right now bandwidth is subsidized by the companies in order to gain market shares. There is a strong competition between access point providers that allows consumers like ourselves to benefit from that competition. But in the long term of things, there is an actual real cost to bandwidth, and that cost eventually, potentially, could be passed on to either the consumer or the service provider in order to do that. So let's continue. If I'm now a movie service provider, and I want 2 terabytes of storage for storing my movies, and I stream 10,000 streams a day because I have about 10,000 customers a day for my movie service, I would be paying $150 of storage cost and $137,000 for data transfer. I need to start thinking about what it means in terms of how much I charge for those videos. Maybe I can put some advertisements in front of it, but the advertisement will have to compensate the $137,000 that I am out of pocket. If now I am a Blu-ray online service, so I'm offering a service that you can go and watch the Blu-ray quality type DVDs out there, so I now need 9 terabytes of HD movie capacity in order to put my 360 discs that are available on Blu-ray right now. They are 25 gig each. And I stream my 10,000 customers a day, encoded at 36 megabit per second, which is the standard streaming of Blu-ray. My storage cost will be $1,350, and my bandwidth cost will be $1.2 million. So the point here is just to elevate some of the reality of things that we are not really seeing yet. And as we will be seeing at the end of the presentation, the goal is not to scare you in any way, but at least to raise the level of awareness of the certain things and what you could do to compensate for some of those numbers. Typically, one is knowing that being the pipe owner clearly has an advantage, since you might not be paying that, since you own and lay the fibers and lay the cables. And potentially shipping Blu-ray by post is not a bad idea after all. And even though you have 1-day latency. So understanding those type of latency bandwidth differences and understanding bandwidth is not latency now start to get some thinking into you, I hope. Continuing here is local storage is actually fairly cheap. Use the Live Search cashback feature that we announced a few months ago, which is a great way of finding stuff and having a rebate and getting some money off your purchase. This is a slight plug. You can order a 1.5 terabyte, there's a typo here. A 1 terabyte drive, the math is good, the typo is on the terabytes, for $132, meaning that you can have you can pay the gigabyte of storage at 13 cents a gigabyte. And what is even more interesting is if you look at the trend, storage cost is becoming cheaper faster than bandwidth cost. So now, for the first time or in the last few months, storage is now cheaper than bandwidth on a gigabyte perspective, and it's going to be even cheaper along the way. Which means that emerging patterns that we might see is a movie service, the one that is paying $1.2 million of bandwidth, might start thinking about different way of delivering their software, their movies. As an example, they can have a local device, call it a edge device, a recorders, a PCs, a set-top box, whatever you. And because they own all the set-top boxes from the movie, they might actually subsidize that set-top box, saving all the bandwidth that they've been not paying. And instead of streaming those 10,000 individual movies independently every day, they might think about using multicast, having one stream, hitting all those boxes at once, and putting, I don't know, the top 20, the top 50 movies pre-cached, put in the local storage using the terabyte there that is available. And when someone goes to the movie service on the website and say, hey, I want to watch Iron Man, or I want to watch this latest movie, I'm not streaming it from the network. I'm actually unlocking it from the local storage. Or taking advantage of peer-to-peer technologies where basically you offload some of your bandwidth costs to someone else, and using some of the free bandwidth somewhat that is out there could be something that's more appealing. Or use, as some companies are starting to think about, non-IP network in order to deliver the content. So non-IP network could be the cable, so using the videos. You can use some of the channels that you have in your video to push some of that information and have the local device to store it from the cable and then unlocking it from an IP network. Or you can use, as I mentioned, the FedEx or Post or UPS way of putting storage somewhere without using the IP network. So there again, here are some architectural patterns that are emerging because of the reality of cost that exists in the bandwidth and latency environment. Here is just another data point for you in terms of you thinking of going global. Those are the IP transit costs depending on where you do them. So basically, bandwidth per megabyte per second in Sao Paulo is about 8 times the cost of in the US. And it's decreasing even not as fast as in other environments. So there again, this is a source that I get from a website. It's quite interesting that monitors the prices and things like that. This is what a network pays another network in order to be allowed to transmit some of their IP network into someone else's network. So you could imagine that those two networks have peered agreements that you basically pay only the difference between the two. So I sent you a gigabyte worth of things, and you send me half of that, so we can compensate. But regardless of how it's done, this is real cost that network providers are paying, and they are at some point have to be pushing that up to the service provider, to the application providers or the end consumer. Another piece of trivia that I think would be interesting is because of the cost of bandwidth is different in different countries, behavior from people is also different in each country. South Korea and Hong Kong, who happens to have the highest bandwidth capacity as part of their ISP providers, tend to be the one who have the biggest consumption in terms of gigabyte per month. Australia, as we've seen, that has a fairly limited amount of flexibility in terms of how much total capacity they give their customers, has educated the customers to be fairly frugal in terms of bandwidth consumption. So I think there is another important point here, which is you cannot expect people to just go to the service and download everything you want them to do. There is some learning, some experience that they've grown into from some education they've received from their paycheck or their bill they're getting from the service provider that modifies the behavior in terms of what they're willing to download and not. Okay, so I guess enough about latency and bandwidth. I think hopefully I give you some good understanding that one has to be at least aware of those. And realizing that if only it was latency and bandwidth, we would be actually in pretty good shape. What is happening in those systems is that things fail, and all the time. And that's another thing that is quite annoying when you're trying to build an application. So let's see some numbers. First of all, this mean time between failure number is something that the manufacturer of components will tell you. Basically, it gives you how long something can last, to give you a way of assessing how quickly this thing will fail. So if you think about simple components like a disk, an Ethernet card, and a CPU, a fan controller, the manufacturer is giving you pretty high numbers. Let's see them. The disk manufacturer, if you go to Seagate or one of those companies, they tell you that the mean time between failure is 1 million hours, which is about 114 years. Okay, let's assume that this is true, and actually it is true. I'll give you the reason why. that the mean, if you have 20,000 disks because you're in a data center with 20,000 machines, you have one disk crash every 2 days. Okay. Now, if you add Ethernet cards as part of the system, and the MTBF of the Ethernet card is 44 years, of course, as we all know, and CPU fan is 22 years, who would have doubted that? If you combine all those probability, it basically means that you have, statistically speaking, 2 or 3 machines out of order every day. 2 or 3 machines out of 2,000 is actually pretty good, except, of course, it's your machine or your data that is on it. So what does that mean? It means that if you are in this big number game, which I understand not all of us are into, but just to give you some understanding of what's happening here, failure will happen regardless of what you do. So you have to design for failure. You have to assume that the underlying environment will break. And it's okay. There are ways of handling this. But before I'm telling you some of the elements that helps you handle failure, I just wanted to go back to the mean time between failure. And actually the definition of MTBF is the reverse, the 1 over the constant failure rate. So any component has these 3 phases in life. You have this infant mortality phase that happens, that has a very higher failure rate when they are powered on the first time. There's some electronic components there that get burned the first time they are turned on and things like that. Then they have a fairly stable, fairly low, constant failure rate for some time. And then there is the wear out phase when things get bad fairly quickly. So the MTBF, and that's why you're seeing the 144 years, the 44 years, and the 22 years, is basically the inverse of this constant rate. So it's true that in that particular constant rate, if you reverse that, you have these high numbers. In order to make this more concrete, if you think of a 30 years old in the USA man has a failure or death rate of 1.1 per 1,000. So statistically speaking, a 30 years old man in the US, 1.1 30 years old man in the US die every 1,000 30 years old man, which basically gives a MTBF of human of 900 years. I guess even in California, with the super healthy organic eating people, there will be hard to reach that number. But the point here is that MTBF is not about lifetime, because the wear-out phase is basically what the wear-out phase is about. It's, statistically speaking, on that particular category, how long you can expect someone to live or to last. So it's much more a failure rate on a distribution than the actual lifetime of a single component. So let's continue. This failure rate is actually not new. I was discussing this presentation with Eugenio, and he pointed me to an old article of the, I don't know how you pronounce it, ENIAC? Well, one of the very first computers that were built, and you can see a picture of it. And it contained 17,000 vacuum tubes, 7,000 crystal diodes and relays, 70,000 resistors, 10,000 capacitors, and around 5 million hand-soldered joints. They also had to deal with failures. Interestingly, is back then, failure was actually more frequent. And this is a quote that I found there, and I'm going to read it with you, is we had a tube fail every 2 days, and we'd locate the problem within 15 minutes. So in 1954, they were very happy because they could have a continuous period of operation without failure for about 5 days. So there again, this is a piece of trivia that is interesting, and saying that dealing with failure, or actually not dealing with failure, is an anomaly in our industry in the last few years. And because of the law of big numbers that we're entering again in the cloud, and the number of clients that or customers we try to reach, and the potentially hundreds of thousands of requests that we're getting every day in our next to be super powerful and super popular service, we need to reintroduce that thinking into our minds. So what to do about constant failure? Well, one hint here is you can dust your old probability book and try to see what probability can help you with. If you look at your probability book, you will see that if 2 events are independent, the probability of 2 things happening is, the intersection of those 2 probability is the multiplication of each probability independently. of course, if those two probabilities are independent. So you have 3 machine failures over 20,000 in total, which gives you a probability of failure of 1.5 per 10,000 machines, which means that if you replicate your data 3 times, so every time you write to something on this 20,000 mega cluster, you write it 3 times, the probability of losing data, if independent, is the probability of failure of disk 1 times the probability of failure of that machine plus the probability of failure of the third machine, multiplied. 3 chances in a trillion. That's actually a pretty good chance. I would actually take that chance on my data. So by just replicating your data 3 times, which is what SDS is doing as an example, you're actually increasing dramatically, and you're basically in the edge cases of something happening. There are more chances of, I think, Earth exploding than that. So I think you're okay. Of course, this implies that events are independent, and they are not. If these data centers, the 20,000 machines are in the same data center, something happening to the data center itself breaks the model. If you're using the same disk batch, maybe the disk itself is broken and the batch itself is broken, so the probability of one being broken next to the one that just was broken is higher. You have the same human operator handling the entire environment, so one red button pushed and everything is down. So the goal here is to make them as independent as possible so that you can benefit from the multiplication of the probabilities. So it's not completely random that actually data centers are replicated using different locations, different teams handling different aspects of the elements, different suppliers, so that you can go and try to not have correlation between one thing happening and the other one happening. Actually, the risk here that I did not count in my trillion risk is the window that is happening while you are replicating the thing. So you are writing to a disk or to a machine. It takes some time for that to be replicated 3 times. While this is being replicated and that thing fails, then you have a higher chances of failing than the 3 trillion. But again, we are just getting generalities here. But this concept has been I've seen on the web people referring to this concept as, what is it? 2 pieces of crap is better than 1 piece of crap. It's just the concept that, even if you don't have the high quality stuff, but just having more of those, it will actually work fine in the end. Another simple example that you can think about is we talk about SLA and availability a lot in the industry. So if you have a 99.9 uptime, if independent, say you have 2 data centers with each 99.9 uptime, while the uptime of the 2 combined is 99.99 uptime. Basically, you have a 10-time uptime increase with a 2-time cost. So you replicate twice, you multiply by 10 your availability because of the probability of those 2 happening at the same time, with only twice the cost. Of course, the problem here is that the independence, again, those 2 data centers might not be that independent or as independent as you would like them to be. And if you need to replicate this, then you have the issues of state, because they're actually not equivalent if you're not replicating things instantaneously. So going back to the window that I was mentioning before. But if it's stateless, it's much easier. And if you think about the log shipping and the disaster recovery things that we do in the industry, they're very much about this. The probability of my data centers failing is such, but the probability of both my data centers and my disaster recovery failing at the same time is low enough for me to accept that cost. Make sense? So why, as I mentioned, why is it not super intuitive? All the things we said so far is that so far we've lived in this, what we call special condition. This special condition happens to be the enterprise data center. The special condition is where you have only few nodes. So data centers today have only a few hundred machines, so a couple of hundred, that will not put you in the numbers that you will have daily or multiple failures daily. Most of the applications there are on LAN networks. So as a first degree of approximation, a LAN gives you, well, not infinite, because infinite, as we know, is a very large number. Well, I was hoping for some fun here, but anyway. 1 gigabit network is actually a fairly robust network to play there, and from a latency perspective is pretty much negligible. And because of those, you have a minimal partitioning of your data. You don't have to think about the distribution of the environment. You don't have to think about the latency. You don't have to think about the different availability things. And so the acid metaphor, as we mentioned in my first presentation, I will be going further in this one, can be applied. So you can think and program in an enterprise data center very often as if you were the only user of that data center. And multiple people using the metaphor of being the only one using it are not too many so that the system cannot scale to your need. But once you go to another order of magnitude, or a couple of extra order of magnitude, this model of I'm the only one using the system, so therefore I can lock everybody else while I'm doing my stuff, is not acceptable anymore. So another quick thing, just we are in the trivia zone here about data centers. What's interesting to note is that power, for those of you who are not familiar with that, is the limiting factor. The size of a data center is not about how many square meters or square foot you have down. It's not about how many servers you can stack up, or it's not about how many other metrics. It's how much power you can bring into the data center. Can you bring 10 megawatt? Can you bring more than this? The amount of energy that you can bring in, knowing that, of course, you have to have a backup of that energy. So if you have a 10 megawatt data centers, you have to have a redundant 10 megawatt source of energy that is not coming from the grid, otherwise you would not be independent, which is, in my opinion, has not happened yet, but is a great way of recycling a lot of those old Russian nuclear submarines. Is basically what limits the size of the data center. So when you start thinking about the size of the data center and energy being the number one concern, and if you add to that for a data center, the cost of it is the server cost, so how many servers you buy to put it there, the electricity consumed by those servers over the lifetime of those servers, usually 3 years, and the facility, so the building and the cabling and the cooling and all the rest that is required to bring the electricity to that particular server, the server cost happens to be the cheapest. So now that you know that, and you know the power is your limiting factor, I'm surprised that not many people are thinking about yet, even though it's happening more and more, energy efficient software. So we know about availability, we know about scalability, we learn our patterns, we read all the books about how to do stateless front ends and so on and so forth. What we haven't learned yet is the energy consumption, and what we haven't learned is making trade-offs potentially between energy efficient code versus performance code. So to be honest, I don't have patterns for this yet, but that's something I think as an industry we will be evolving into, and not necessarily only about green IT, which I think it's a good thing not to completely waste our planet in 20 years, but from a real dollar impact, because the limiting factor is the power to the data centers and the lower cost, the bigger cost of it is electricity. Having algorithm, when you code your environment, something that you can actually flag or some metadata there or something that say, hey, I could do this more energy efficiently, or I can do this more performant, to at least have an educated decision there. I'm not saying that you should go all the way one way or the other, but at least thinking about it. Of course, one thing that I hope will happen from a Microsoft perspective, from a platform perspective, is that a lot of those things will be built in the underlying platform. So not every single developer will have to think about those issues, and maybe you can write your ASP.NET code and things like that, and then metadata associated with that will basically tell you how you want that particular code to be run. All this is science fiction right now, but just to elevate some of what we might see in the future, I think this is something that maybe some people in research are doing, or some people have done on a proprietary fashion that might end up in more platform products. Another thing which is interesting is that people are the #1 cause of outages in data center. It's not about the network, it's not about the servers, it's not about the bugs. Data centers go down mostly because of the people running them. So how can we remove this little inconvenience of having people around? Well, that's another big topic in large data center and in the cloud space, is automating everything and really thinking about 9-to-5 management. 9-to-5 management, I'm sure many of you have heard of it, is this notion where IT pro people and operation people don't have beepers anymore. They're not on call anymore. Because if they were, they would be there all the time because of the failure that we talked about. So here, 9-to-5 is another way of approaching and understanding that failures happen. So when failure happens, it's just fail. And the system is redundant enough and knows how to behave with failure so that an operator can come at 9 o'clock in the morning, look at everything that has failed, all the machines that are not working anymore, going there, taking them out of the rack, taking a new machine that is working, putting it back in the rack, do that for 8 hours a day, or whatever it's needed, and then go home. It's not about troubleshooting anymore. It's not about fixing it. It's about taking what is wrong, moving it out, putting something new, and then have that batch of broken machines either fixed or sometimes not even care about those. Just use them for something else, parts, and reusing some of the elements. So that's again a change in the mindset of how things are done. I don't think enterprise data centers today are really 9-to-5 management things, and I don't think the automation around data centers today in the enterprise are of that nature. There are good reasons for that. As we saw before, this local special case might not require it to happen, but if the technology that has been built for these massive data centers were to move back into the enterprise data centers through platforms, components, and things like that, I would imagine most of the enterprises wanting to approach the problem this way. So let's continue. Let's travel towards all those issues, hoping that it's something that is of interest to you. It's been a lot of fun building this. Hopefully it's as fun for you to listen to it. High school math, which I've learned a few years ago, is telling me that if a function is linear, then if f of x is linear, f of a times x is equal to a times f of x, which basically says that linear is good. Why is linear good? Is that if this f of x is the cost per concurrent user, and f of x is linear, the cost of 10x users equal 10 times the cost of x users. Because a lot of the revenue is linear, so if you're monetizing your environment through advertisement, CPM, cost per impression, or even cost per click, or subscription model, usually there is a linear correlation between that monetization and the number of users. So if your revenue are linear, but your costs are not linear, it will basically break you. The more customer you have, the less money you make, because in order to support those non-linear growth, you only have a linear growth in your monetization. So the goal here is actually having, for every extra customer you have, having a per customer cost that is lower than the previous one, as opposed to a bigger one. So here is a news for you. Scale up is not linear. The price of scale up just is linear up to a certain point, but then bigger machines and bigger things end up costing more than the same amount of power, the same amount of energy, the same amount of disk, than 5 times, a fifth of that machine on 5 different machines. Which means that you need to scale out. you need to scale out, which means that you need to be tolerant to partitions. Your system is not running in one box anymore because of the reason we just described. And if your thing is not running in one box, you need to understand what happens when you're running in more boxes. And I bring back what I mentioned in my first session. For those of you who were there, there will be some repeat, not too long, but a little bit of repeat. And for those of you who were not in my first session, this is a theorem or a conjecture saying that by a professor in UC Berkeley who was the founder of Inktomi, saying that out of those three capabilities, you can only have two. So if tolerance to partition is a given because of your scale-out choice, you have to decide whether to go with consistency or availability because you cannot have both. So the CAP conjecture of theorem, I don't know if it's been proven yet, but it doesn't matter because in practical terms, it's actually real. We are in the, which one is it? We are, which one is it? Availability, okay. Is the first one where, no, I'm lost now. Anyway, we have those three things, and basically means that in order to be one or the other, you have to be understanding consistency versus, am I going back? Yes. So again, and I apologize for the one who have been here with me the first session. This is only the only one that is actually a repeat for the first session, is going back to these examples of the shopping cart, where you have to basically decide whether you want to be available, so basically having the shopping cart always ready for you to write stuff in, or you want to be consistent, meaning that you have to lock on resources, making sure that what you put in the shopping cart is actually available to you from the inventory system, which itself checks that from a distribution environment, which itself checks from the ERP system that everything is okay for you to put it into the shopping cart. So here the idea is, again, going through the life cycle, I'm going to go fairly quickly this time, is that while you're shopping, you really want your system to optimize for availability. You don't want anything to prevent someone to put anything in the shopping cart. So you will be writing your item or your entity into the shopping cart regardless of what's happening in the back. You're not caring about consistency as much. Once the shopping is over and you grab item from inventory, then you need consistency because you want to have a fair understanding and a true view of what the inventory number is. And then when it's shipped, the data is become read-only. You can put it in a different way and managing it differently. So here the point here, the same tool for each is not optimal. So understanding the data is different. Understanding the notion of availability versus consistency is an important one because more and more it's going to be likely that you will be scaling out not only the computation element that people have been scaling out forever, the website and the web farms, but the data now, we are at the level where more and more applications will need to shard the data in multiple elements, and therefore you have to do and approach it in slightly differently. So here is a quote. Actually, before I see the quote, is that this example of eventual consistency are actually very real. Swift payments in the banking environment, stock market trades, airline reservation, even ATM in many cases are not consistent. Eventually, they will get consistent, but at the moment you do that, at the moment you buy an airline ticket, as I'm sure all of us have experienced, it's not a guarantee you actually have a seat. You actually buy a tentative seat on that plane. And they have some heuristics and they have some overbooking management also that allows you to deal with that. But if they were in the Sabre system and all those massive reservation systems, they would have to check the actual inventory and lock multiple requests to that inventory before giving you back the things if you have that. It might not work. So they're working with cache data, they're working with heuristics, they're working with other ways of assessing what that element can do, but most likely most of those systems will actually always allow you to write into them. There are exceptions, there are ways of doing things separately differently, but as a general model, what my point was, it's not new. People who have been in situations where massive distribution and massive scale is required, they've been doing this for quite some time. And here is a quote that I like that I found the other day on the web, and I'm going to read it with you. So Flickr, you know Flickr, the very popular photo sharing environment, anticipated this design, this cap design, as I mentioned earlier, in their architecture when they chose to duplicate comments in both the commentator and the commentee user shards in the data storage, rather than creating a separate comment relation. I don't know how the decision was made, but it must have gone against every fiber in their relational bones. So in order to, instead of having one comment and having the commentator, whoever write the comment and wherever the comment is about, pointing to that comment, they're actually duplicating the comment on both sides. And if the comment is changed on one side, which is very rare, well, you might have inconsistency, or you will have a replication of that comment eventually. But at least you can go, they simplify tremendously the system that actually is managing comments, which is one of the biggest bottlenecks that you had in that particular environment. So going back to the eventual consistency element is something that I mentioned again, acid versus base, different approach to data, and realizing that sometimes it's okay to be wrong. It's actually cheaper to be wrong sometimes than to be always right. Another example from the e-commerce world. Let's assume I'm buying a Harry Potter book. Most of the people going there and buying the Harry Potter book will get a copy of the Harry Potter book because the stock of the Harry Potter was such that they were anticipating the demand. If they had to check that there was this Harry Potter book every time someone was buying it, it would have required a much larger system for handling the 10,000, 20,000 concurrent users on that system. So they basically assumed that the thing was there and they accepted the transaction as such. And in the maybe event, very rare event, that the Harry Potter was not available for the very few edge cases, well, they notify the user offline. They might send an email, they might wait for a complaint, and for that particular user, maybe they give the Harry Potter book for free. They say, hey, we're very sorry, you should have gotten it, I don't know what happened, how about I'll give it you for free, and by the way, here is another book that you can pick from me, and we're all friends like before. Well, giving a few Harry Potter books once in a while to people is much, much less expensive than having an infrastructure that has to cope with 10 times the load when everything is locked and consistent. So there again, something that is actually quite interesting from an architecture perspective is that when things starting to get hard to do with a certain architecture, one could step back and say, what can I do differently? Can I think about the end-to-end transaction in a different way, as opposed to optimize my particular environment here, which is making sure that a Harry Potter book is available when I buy it, by stepping back and looking at the fact that, hey, maybe it doesn't matter if it's not there, if I can find a way of compensating this, it might be a better way of approaching the problem. Another thing that I wanted to share here is that the authentication is actually a key element. There's a lot of things you can cache, a lot of things you can do later, there's a lot of things that you can have eventual consistency with. The authentication piece is actually a hard problem. Having availability consistency is actually a very tough one. It can be done. I don't know, I personally don't know where to go. I would actually tend to optimize for consistency and authentication, basically because I don't know sometimes the risk of authenticating against cache. A lot of authentication algorithm and scenarios use a cached version, but basically you're exposing some level of risk by authentication the cache because the cache might be invalidated at a moment that you actually don't know about. So just elevating the authentication is actually a special case that is worth spending more time on. Okay, that concludes another piece of the presentation, and what I wanted to do with the next section is actually run, even more numbers, just to see what happens. And I think those are interesting numbers to look at. We talk a lot about software as a service and subscription models and things like that. And let's see the financial statements of some of those companies that actually are delivering their software as a service. So, and starting to understand the notion of subscriber acquisition costs and churn. Something that the telcos, wireless providers, cable operators understand very well, but usually software providers, service provider, ISVs, are not very familiar with, but if they're entering the service-based world, they will have to think about that particular aspect of the business. So let's see. The numbers we will be seeing are based from a public SEC, this is a public company offering software as a service, and I looked at the public filing that they need to do as a public company quarterly and play some numbers with those. It doesn't matter who it is. If you really, really want to know, I'll tell you maybe at some point, but it doesn't matter, it's just the concept that matters. And just one hint, it's not Microsoft. So let's see. The total revenue for that particular software vendors were $263 million, and the cost of that revenue were $54 million, which basically is a gross margin of 79%. That's pretty good. It's a good business to be in. However, if you look at what's happening after the gross margin, the sales and marketing was $131 million, which is basically 50% of their gross revenue was going into marketing. That, not so good. Which, after all expenses and everything done, the net margin is 4%. And again, it's not a critique on the business model, it's not a critique on that particular company. It's just to show you some points that I'm going to make later, is that for that particular business to work, they need to acquire customer all the time. They need to go out, and that's where the sales and marketing goes, is that they need to go out and acquire customer because they're actually churning customer at the same time. Software as a service, not locking you, or actually not having your money up front, expose you to a longer time for your customer to disappear, and that time that you're exposed, which is called churn, is something you have to deal with. So what's also interesting in this particular example is that those 4% margin is actually lower than the Orange CD certificate of deposit that I could get yesterday from Orange at 4.25%. Just actually interesting to, and this is safe, well, used to be safe. I think it's FDIC insured, so if I spend less than $250,000, I think it's okay. Anyway, going back to the point here is revenue is not profit, we know that. But let's look at this subscriber acquisition cost, which is something that I know as developers or architects we don't really care too much about, but I think as a way of concluding PDC is a nice extra piece of trivia that makes sense to know, is that this particular company, with the number we saw before, has a total 47,700 customers, which an estimated seat of about 1 million seats. So that's how they make their money. And the new seat, the new actual paying subscribers that they acquired last quarter was 110,000 new subscribers. And we know that the average gross revenue per seat per month for that particular company is $54. Knowing that, and knowing how much they spend in sales and marketing, by dividing the amount of money they spent in sales and marketing to acquire those new customers divided by the number of customers they acquired, they basically have spent about $1,189 per new customer, but making only $54 a month from those new customers, which basically means that they're exposed for 22 months. If that particular customer leaves that particular service before 22 months, it costs that particular company more to acquire it than the revenue that were taken off that particular customers. 22 months, is it a lot? Is it not? Well, I don't know. We'll see. Let's see the impact of a churn of 10% monthly. So 10% monthly is a lot. It means basically that every month you lose 10% of your subscriber base. It's much more than what you could expect, but if that was the case, then they would start with these 110,000 new customers. They would have paid this amount of money to acquire them, remember, 1,000 each. At the end of the 24 months, they would be losing $75 million. This is not reality, this is just what would happen in this hypothetical case. 4% churn, this is maybe more realistic. Still ouch. Still losing tons of money. So if reversing this formula, the break-even point is at 0.8416% of churn monthly. So this is actually by making no money, they need to lose less than 1,000 customers a month. So out of 110,000 that they have, if they lose more than 1,000, more or less, they're not going to make any money over 24 months. And again, this is just mathematics. In theory, people can pay forever and people stay long. But the point I'm trying to make is that the notion of zero churn, which would allow this particular company to make $13 million net out of those particular customers, is not actually very realistic. So how do you think about churn? So from a business perspective, you can have longer-term contracts. This is basically what's happening with cell phones, providers, and so on and so forth. You lock your customer for 24 months. There is no churn during this 24 months unless there is penalty. But of course, it removes some of the value proposition of the service. A lot of the things we hear in the software as a service world is, hey, why don't you come in, you test it, you go back, and I don't really, if you don't like it, you can go. Here is basically saying, hey, you can be my customer, but you have to sign for 24 months. It still works, it's still very acceptable, but it reduces some of the value proposition. And often when you have long-term contract, when the contract expires, and we see this a lot in the cell phone industry, where basically you get the new shiny phone, you have to lock with the provider for two years, and at the end of 2 years, you either have to reacquire that customer by providing a new subsidized phone and having 2 years worth of contract, or that particular customer goes somewhere else. So another thing which actually quite interesting is try to get the money up front is a technique that is actually not very bad because you are now churn insensitive. If you get your money up front, then of course people leaving is not as dramatic as if they were leaving by getting the money one by one. The other one is lowering the software acquisition cost by building distribution channels, white labeling of your solution. So basically you pass the acquisition cost to your channels in some respect and making some arrangement there. And obviously some of those channels get compensated by providing you customers. This is typically what some companies have done, and I'm not going to go into those details. Another one from an architecture strategy is actually having a client strategy. It has been shown and proven that if the service you're offering is combined with something you actually install on a machine, or that has a device like a phone or a heart monitor device or an appliance that you install at a customer, the likelihood of that particular customer leaving you is much, much reduced because there is an upfront investment on that particular client strategy. And the service, you can monetize your service in the back the way you've been doing it with a much lower, riskier environment because you have much lower churn if you have a client strategy as opposed to your service model. Does that make sense? So again, the idea here is not to do an MBA or even a sort of business discussion here, but I think it's interesting to realize some of those concepts that are often not put in the forefront of new technology here. And then my final section is like, there's actually other things one has to think about, and people say, well, there is more, but there's already this and that. Well, it's the policy consideration. Here, I got that from a colleague of mine, Jim Miller. And Jim, if you're in the room, thank you. It's basically realizing that there are some regulation out there that want us to comply with. So let's take an example. I'm a French lecturer. I don't know why Jim decided to make the lecture in French, but why not? So this French lecturer is going and visit China for, assuming, providing some lecturing services, teaching at a university or so on and so forth. And let's assume that this particular lecturer is using a US-based server hosting third-party service, and in order to get to that, it's actually caching some of the data in Japan. Very common scenario in this environment. Something that I cannot answer, maybe Jim could in a full session, but things that we need to be aware of is basically what laws apply here. Is there anything encrypted? When? Who holds the key? Who retains the information? For how long? What can the Japanese caching company do with the data? Can they look at it? Can they not? What are the regulations of the US? What are the US laws that might prevent or allow this thing to happen? What about the copyrights? Obviously, if it's personal identifiable information, there are very strong European laws that I know of that dictate some of the things you need to do. I'm sure there are many laws about this in many other countries. I just happen not to know them. So where to put the data, you have a technology answer. You want the data near to your customer. You want the data very near to power and telecommunication hubs because, as we've seen, you need a lot of bandwidth and you need a lot of energy for running your service. And also, you need to put them close to a content distribution network because, as we know, of the issues of delays and latency and bandwidth and things like that. However, the legal issue might dictate otherwise. And again, I'm not a lawyer, thank God. But there are legislation here that need to be taken into consideration, which I don't know much about, but US laws requires repatriation of data. You cannot do foreign wiretaps in the US, so depending on what you're actually doing in between, you might be following under that particular law. Some countries tax all corporate income if any service facilities are in the country, so you might be deploying some stuff there and that might be considered as actually operating the service in that particular country. That might open some tax liability for your service. And obviously, if you're part of the healthcare system, the banking system, or other systems, you have auditing and measurement, SOX, Basel II, whatever compliance that you have to go through. So the net result between the technology and the legislation there is that it's already hard to decide where to put the data just from a data center perspective. It's even harder to think about the data when you start introducing personal information. And also there is a lot of ongoing processes and money that has to be there to comply to the various issues that the legislator imposes you. So unfortunately, I don't have much answers for this one. And it would take a full session just in answering those, but just to give you an extra sort of feeling of what's happening out there. So in a nutshell, there is latency, bandwidth is not infinite, it is not free, things fail all the time, business models are a mess, policy are in the way. Why are we doing all this? And so the reason I put that slide in is because I wanted you to actually come out of this with a positive note. And the positive note is that if it's done right, if you understand the issues and you do them in the way they're supposed to do, real magic can happen. There are services, there are functionality out there that we could not have dreamed of. There are a possibility of communication, connecting with parents, connecting with children and grandparents, doing business with people we've never done before, expanding to geography that we were dreamt to expanding, lowering the cost of doing all that. But one has to embrace the new model that one has to follow in order to achieve this magic. So really what I wanted to do here is not to scare you by any means, actually very much the opposite. I wanted to make sure that you are very bullish and very positive about the cloud opportunity as much as we are, and encourage you to embrace this new model with all your energy and all your intellectual capacities. But making sure that you do this right, understanding the business models behind it, understanding the architecture that are behind it, because the technology is actually finally here. What you've seen the last few days, Windows Azure and SDS and the Live and the Mesh and the things, Windows 7, the Office web app, and all these kind of things are really new components that allow you to embrace the cloud in a way that it was not possible before. But just making sure that when you do this and that you can finally take advantage of very strong platform assets, that you are aware of those architectural and business challenges that even though we are developers, we are architects, we're not the business owners, we need to be participating in those conversations. Because maybe we might be the only one knowing about those. By the time those suits will understand that problem, we will have solved it for them, which actually could be good for us. So with that, I hope you gather good trivia for your next cocktail party. You can now, say, hey, did you know how much it costs to ship some Blu-ray over bandwidth and things like that? And certainly, it's been a pleasure to be part of the PDC. And with that, I would like to thank you, ask you to fill out the evaluation forms. And of course, we have plenty of time for Q&A and And I'd love to get your comment about this. Thank you. Yes, please use the microphone so that people can hear.
I noticed you did some of the statements about.
Can you talk in the? Sorry.
Hello?
Yes. Sorry. Yeah.
When we went back there and did some discussion about linear, about linear patterns.
Yes.
And linear is good.
Okay.
Are there circumstances out there where the distribution is actually logarithmic, where the more people use it, less it costs per person?
Well, if you are not if you're a nonlinear business, if a nonlinear architecture.
Because there's nonlinear, which is exponential, which is bad.
Well, yeah.
And then there's logarithmic, which is something else.
Correct. So linear is good. Logarithmic is even better.
Yes.
I agree with you. I haven't really thought about this way. And if you have architecture that actually are logarithmic in nature, it's fantastic. But yeah, very good point. Yes?
Hello.
Yes.
Our company develops software for a European bank, so the legal issues around cross-border communication and so on are very important for us. Does Microsoft provide currently some legal support of the cloud in computers, or do you think what is your model about this?
Well, the thing is, as of today, we are very early and nascent in the cloud computing platform. So we are first introducing the platform in terms of storage capacity and things like that. So something else that I wanted to make sure that you understood is that we as Microsoft are aware of this issue, and it's going to be important for us to not have everybody solving their own problem individually, but trying to generalize those problems and push them into the platforms. This said, as of today, there is nothing that you could use from our environment that is certified for a certain process today. But why not? I cannot see the future, but it would not be unlikely that there will be some certification around some of our assets, and they say, hey, if you're using this way, or if you're storing that information that way, then we are certifying the processes to be this, and that. I think this is very important for a platform company to offer that. Now, something that I said earlier, we need to make a differentiation between where we are today with the bits that we announced at the PDC and what we're going to be in when we're done. Mm-hmm. Anticipating those trends is good. When you're going to be going home and playing with the technology we have today, you're not going to see this yet. Mm-hmm. But I think it validates the point that those are platform assets that need to be built in that goes beyond the pure technology. Is how can I build a platform that is aware and friendly to those business models, that is aware and friendly to those privacy concerns, that are aware and friendly to those policies things.
Mm-hmm. May I ask you another question?
Go ahead.
You have been talking about non-linear dependency. So are you planning to compensate for this in your subscriber model for cloud computing?
Well, I'm not sure where you would see the relationship there.
I mean, it's a risk for us that this
we are not
a risk for us. So if you can compensate for this risk, it would be interesting for us.
Okay. Okay. Well, I don't see the pricing going exponential in any way. That's against the model we have. But yeah. Okay. It's a good feedback.
Thank you.
Question, sir?
So this might be too data specific, but we don't see a huge likelihood. I mean, a lot of us have played around with object databases, and the entity-based models for data storage are, well, they're not relational. Mm-hmm. And we have a hard time seeing how you're going to truly move a relational model into the cloud. We have, I don't want to be doing queries back to my origin servers, if I'm keeping my databases there. But on the other hand, our data models are so specific that we just have a hard time seeing how you're going to actually make that real.
Well, there are multiple ways of approaching this. As I mentioned, I don't know if you were were you at the first session by any chance? No? Okay. So I touched upon a little bit of that, but I'll reply. One thing that I want us to understand, and I think it's very important to understand, it's the cloud is not a replacement to the server. The cloud will offer new ways of approaching data And there is a differentiation between SQL Server, as an example, hosted SQL Server, and a new cloud fabric. Microsoft will offer the three of them. So you will be deciding the programming model that you want to use. And if you want to use the SQL model, store procedures, triggers, relations, tables, joins, and things like that, then you should be comfortable with SQL and potentially some sort of hosted SQL thing. If you're willing to relax some of those models, so maybe you be willing to relax some transactional integrity, but gaining massive scalability or potentially gaining an order of magnitude in cost per gigabyte, because what you're doing might not be transactionally sensitive, such as uploading a picture to a profile website or streaming a video, things like that, then you're going to use that. So you're going to see as a spectrum of offering. And I was discussing with a bank not too long ago, and they were saying, oh, I'm doing my web e-banking site will never use the cloud. How could I? I said, well, maybe you're right. Maybe you're not. I don't know. But let's look at it. And quickly we realized that the e-banking site was at least two separate sites. There was one that was the transactional aspect of it, so opening an account, transferring money one to the other, and that most likely might not be hitting the cloud as a first-class citizen as of yet. But there was a lot of stuff in the e-banking website that was about new products, videos of people using the new products, commercial things like brochures and things like that, that are perfect to store out there where there is content distribution network, where the storage point is lower than the transactional element that you have. So at the end of the conversation, we ended up realizing that maybe not the entire site will be moving to the cloud, but part of it. And all the videos that are streaming, all the brochures that are putting on the website, all the things like that will be one way, and the transaction will be there. And maybe over time, there will be opportunity for even more optimization and say, hey, as part of my transactional things, I don't need to be transactional immediately. Maybe I can put that on a queue and reconcile the queue at the end, because I don't allow withdrawing from a deposit for at least an hour before the deposit, as an example. Some banks do that. So if you transfer from an account to the other, you cannot withdraw immediately after having joined. So I don't know if I'm answering directly your question, but I think it's worth looking at the problem with a larger spectrum and not thinking about how do I replace what I have with that.
It's just an extension of his question, you know.
Can you close a bit closer to the mic?
Yeah, I'm sorry. It's just an extension of what he asked. I mean, it's understood that it's not an either-or situation between SQL Server and the SQL data services, at least with regards to, you know, moving your existing data or apps to the cloud. But say as a startup ISV, I'm building my, you know, solution from scratch, say some sort of an e-commerce website or whatever. And Windows Azure, you know, is an attractive platform to me, you know, where I can just buy processing power, you know, on the tap and without investing into my own infrastructure and all that. So the code that I write, you know, I write it, you know, to run on that platform from day one. But at the same time, you know, I feel that I may be limited by the capabilities of, you know, the storage on the cloud, you know, in terms of, you know, all the things that we know. So what would you recommend, you know, what kind of best approach you would recommend?
No, I agree with that. So let's be clear again. What we have today is not what we will have in the future. So things can change. And in being perfectly honest, having played with those technologies for quite some time, Windows Azure storage or even SDS is not the equivalent of hosted SQL today. Right. So you need to approach it differently. So there are good things in that. There are good things in understanding those are different fabric underneath, and I need to use them differently. Will we have eventually the hosted version of SQL equivalent? So SDS, for instance, added joins within the same container a few weeks ago. At the very beginning that we were using it, you did not have that. Now you have. They're putting reporting services. So the evolution of it will making it look like and being closer and closer to it. As of today, if you look at the snapshot of October 30th, you will have to consume data and create data differently one way than the other. There's good and bad in that, because you think of it as a replacement. If you think of it as an environment, but to your point of how can I write once and deploy everywhere, we don't have that thing yet. Will we have it? future will tell. But certainly from a developer perspective, the programming models have to be merging over time. The tooling has to be the same. The .NET things have to be the same. So there is certainly a direction into that things. But
just a small addendum. It's not about writing now something that will work, on any model tomorrow. I understand that, the database on the cloud is yet to get there, and eventually it probably will get there. My question is more, what would be a best practice, approach if I were to write a solution as of today, keeping in mind that, later I want to be able to, leverage the full power. So,
okay.
Yeah, I was asking more from that perspective.
So there are more generic things, and putting indirection points, and some of the things that Eugenio did in one of the things in the past is basically you could imagine to write to your own repository class, and the repository class might have multiple implementations based on what storage underlying system you use. But that could also then force you to have the common denominator among the multiple things. So it's very hard to provide a best practice, broad brush thing. I think there are things, I take that as a feedback, as a way of making sure we have that sort of knowledge. So one of the things that we need to do now, certainly in my team and certainly at Microsoft, is being more prescriptive in some of the guidance we offer. Because I think now that we have the technology, that people have technology in their hands, there will be a lot of requests for how to use what and when. And we have some already, we've done some work, but we'll see. But thank you for your question. I think the last question, sir?
So on the point about efficiency of code,
yes,
in terms of consumption of electricity,
yes,
are you thinking of things beyond just simple efficiency of code, kind of standard things you'd be doing now? Or are there specific sorts of things that could, save power in terms of when you're writing your application?
So again, as I mentioned, I don't know exactly what it will mean, but something we do for sure at Microsoft is that at least we measure the power consumption of each individual servers, so that we know the actual consumption over time, and that can be an input in terms of what was running there and then compared to the energy that was consumed, and we can have correlation between the type of software that is written and the type of consumption that is there, so we can optimize that, and realizing that some assets consume much more than others, and try to address those first. The other one is thinking about, things like could lower the CPU clock, things like memory. Using some, you can trade some of the memory for disk storage. You can potentially swap more. So I don't know, I'm making up things right now, so I don't know exactly. But maybe there will be patterns, and even better if the platform does that for you. As I mentioned, I think it's better if you code the way you are comfortable with, and then have the underlying environment say, hey, those are the 2 or 3 ways I can run that for you. A little bit like your laptop. You want your laptop to be balanced, to be optimized for power, optimized for things. Well, if you can do it on an OS level, you could potentially think of it as at a higher level. Does that answer the question? Okay, thank you very much.